back to JAX London 2020. The last session of the day is by Jason Tatton from AWS. Hi, Jason.
Hello there.
Okay, so we have the swap card chat as always. So if you have any questions for Jason, he will answer them at the end of his talk. And now, Jason, let's hear about Concurnas, a modern JVM language for modern software.
Great, thank you. So we shall now begin the presentation. Hello, everyone. This is a talk about Concurnas. Concurnas is a new programming language which runs on the Java virtual machine. Launched in 2020, it is specifically designed for making concurrent and parallel programming easier and more accessible for both software engineers and for people who specialize in other fields. So, who am I? Well, I'm Jason. I've been coding for a little while. I began my career working in finance, where I built and ran teams of people building automated and high-frequency trading systems for banks such as Deutsche Bank and JP Morgan. I created Concurnas between 2017 and 2020, and I currently work at AWS in the Corretto team. Amazon Corretto is a no-cost, multi-platform, production-ready distribution of OpenJDK. And here are some links if you want to get in touch. I want to now cover the motivations for creating Concurnas, but before I do so, I'm going to discuss a topic which at first appears to be a tangent, but is actually very relevant to that motivation. This is the planet which we inhabit, Earth. Of all the planets orbiting the hundreds of billions of stars in the hundreds of billions of galaxies in the known universe, this is the only planet which we know with certainty is capable of harboring life. And all was good. For millions of years, life on Earth persisted, and all the plants and animals each became perfectly adapted to their environments, each living in effective harmony with one another, all ideally balanced, every creature in its place. And then along came us, mankind. In fact, there are almost 8 billion of us now. We are everywhere. We are the dominant species on the planet. And we have achieved a great many things in our time. To feed this ever-growing population, we have cultivated crops. We have adapted and created other species of animals. These are cows, but cows didn't always used to look like this. Thousands of years ago, their ancestors were great big woolly things with massive horns. It has been through generations of selective breeding that these creatures have come to be. And we have created for ourselves vast, glorious cities full of all of the conveniences which make life worth living. This is civilization. We have even probed the innards of the atom. We understand nature. We're able to use nature to improve our lives. But we have also become the abusers of nature. We have for some years now begun to see the impact of our behavior upon the planet. For example, the destruction of the rainforest, which seems to be happening at an ever-accelerating rate. This is biodiversity, which will never recover. This will never come back. Much of this destruction is caused by our over-reliance upon burning of fossil fuels and the dumping of vast amounts of greenhouse gases into the atmosphere. That's carbon dioxide, methane, nitrous oxide, and various industrial gases. We're seeing rises in global temperatures, and this is having effects such as the polar ice caps melting, which increases sea levels, and things like coral bleaching, again destroying a vulnerable and precious part of nature which has taken millions of years to come to perfection. And this is having very real effects upon us with the increases in instances of wildfires and more extreme weather conditions. And we really must do something about this. This is a chart showing the change in global temperatures since just after the Industrial Revolution, when we started burning all the fossil fuels. The orange is a prediction of where global temperatures will be in just 80 years' time. 3 degrees is what we're looking at if we carry on in the way in which we have been. 3 degrees would be disastrous for the planet. Just 1 degree is bad enough. And you can forget the millions of years that this sort of change would normally occur at. This is happening suddenly in our lifetimes. So what does this have to do with computer programming, specifically Java and software innovation? Well, it turns out that computing represents roughly 1% of humanity's global power consumption. But as our reliance upon technology increases, this is a figure which is set to grow. Now, we can satisfy that demand to a large extent via the use of green, renewable energy sources or even nuclear energy. And there is hope on the horizon from things like nuclear fusion and thorium-based nuclear reactors. But one thing we can all do right now, today, to combat that climate change as software professionals is to avoid wasting the resources we have access to. And that comes from using performant and efficient programming languages and runtimes such as the Java virtual machine. Generally speaking, more efficient, optimized code not only runs quicker, but uses less energy. And for a large time, software engineers have had to trade off between using performant but relatively low-level, hard-to-program languages such as C or C++ or even Java, and productivity-oriented but not very efficient high-level languages such as Python. And so Concurrency has been designed, as you shall soon see, to give us the best of both worlds, to provide that energy-efficient performance whilst also prioritizing programmer productivity. Now, traditionally, with any talk about concurrency, there is usually a slide at the beginning about the end of Moore's law and how chips aren't getting any quicker. And this chart of microprocessor performance since the 70s usually comes up. So I'll skip it for now and give you the long and short of it. The modern software engineer is now obliged, usually, to perform concurrent programming in order to maximize hardware utilization. We are now in the multi-core era. And yet, that concurrent programming is quite hard. In fact, many experts estimate it to be the most challenging aspect of modern software engineering. Furthermore, we now have access to GPUs for parallel programming. GPUs use far less power per unit of compute relative to CPU-based computing. Concurrency provides first-class citizen support for both of these aspects of modern hardware. Running on the JVM and compatible with existing Java and JVM language code, Concurrency has also been designed to be usable by modern software engineering teams. Modern teams are not just made up of software engineers, but a diverse range of individuals whom things like domain-specific languages can be very useful. Concurrency also has support for this. So let us begin with the obligatory hello world. And here is the output that we shall explain shortly. At first glance, people say, well, this looks a lot like Python, but with braces. And yes, that is the intention. There are a few interesting things going on in this slide. We have a function here, which is for calculating the greatest common divisor of a number and 3. Functions may exist in isolation. That is to say, they do not need to exist within the context of a class definition, such as in languages like Java. Notice here that no return type is specified for this function definition. This is because Concurrency is able to infer the return types of functions, though, of course, should you wish, you can explicitly define the return type. Here also, the type of y is also inferred. Concurrency employs type inference in order to present the facade of a dynamically typed language, whilst also preserving the safety and performance that comes from a strongly typed language. All types can be used within the context of Boolean expressions. Concurrency has support for tuples. Notice here that the return statement is optional. The final statement of any block of code is considered to be the return type of that block. If that block is attached to a function definition, then the return value of that function is that final statement. Here, we have an example of a numerical range expression iterated in a for loop. And here we have the bang operator. The bang operator creates a concurrent isolate, which you can think of as a lightweight thread capable of concurrent execution. Here we're simply calling our greatest common divisor function but you could imagine a more complex, time-consuming operation in its place. We're going to be exploring the concept of isolates in a lot more detail very soon. We have all sorts of conveniences built into the language. For example, we have string formatting here. Concurrency runs on the JVM and is able to leverage the power of the standard Java class library. Here, we're using the standard print to console. Of course, when you run this function, your output may vary. The reason being that the scheduling of the individual isolates spawned by use of the bang operator is non-deterministic. We'll now look at the language and a little bit more detail. We don't have time to cover the entire language, so for now we'll just summarize the core features which it supports, and there are a lot more, but these are the major ones. Concurrency is a multi-paradigm language. Starting with the imperative programming paradigm, as we've mostly already seen, Concurrency supports the standard feature set here, such as assignments, expressions, control statements, etc. Concurrency also has extensive object-oriented programming support, including innovative new features such as traits. Concurrency is a null-safe language, and it has built-in dependency injection framework, which we call object providers. Concurrency has support for functional programming, including lambdas, function references, list comprehension, and pattern matching. And Concurrency has support for the new emerging reactive programming paradigm. For the remainder of this talk, we shall be focusing upon object orientation, null safety, and concurrent and GPU programming support of the language, as well as its support for DSL and language extensions. So, let us begin with concurrency and parallelism. I believe that there are two forms of concurrency: implicit and explicit concurrency. Explicit concurrency is where we wish to perform a calculation as fast as possible, utilizing all the resources we have access to. For example, gene sequencing, weather prediction. Implicit concurrency is where we are obliged to write programs in such a manner such that we can process more than one thing happening literally at the same time. For example, a stock trading system connected to multiple trading venues, or a self-driving car with multiple input sensors and output systems to drive. Concurrency helps solve these two aspects of concurrent computation. Concurrent programming through the thread and lock-based model of concurrency expressed by many modern languages, including Java, is quite hard. With concurrency, things are different. Concurrency in concurrency is achieved through the use of isolates. What we're trying to do here, and the ideal case really, is to present a model of concurrent computation which allows people to code in a single-threaded manner and to use all of their favorite mutable data structures and algorithms on mutable data structures which they learned in Computer Science 101 and proliferate the internet. You could think of isolates as lightweight threads. Effectively, the number of isolates we can create in a program is bound only by the amount of memory the machine upon which we're running has. We're not restricted by the operating system or virtual machine's hard thread limit. When Concurrency starts, it will create a number of real threads contingent upon the underlying hardware capability of the machine upon which it is running. Isolates then get multiplexed onto these threads. Isolates will copy in their dependencies, and this avoids sharing of mutable state. In this way, they are said to be isolated. But this in and of itself is not massively useful. Isolates need a way to break the isolation rule in a controlled and thread-safe manner in order to communicate changes of state. And hence we have refs, which are a little bit like futures in Java or channels in Google Go, and they are built directly into the type system. Isolates themselves are able to return refs. Here, we're using the bang operator. We are creating an isolate which happens to return a value captured in a ref. This code in isolates here and here executes concurrently. All concurrency code runs within the context of an isolate, even this root code above. Isolates are cooperative. Isolates will yield execution to other isolates. And when they get to a pause point, the line below is an example of such a pause point, it will pause and wait for a return value to be placed upon those refs before carrying on with execution. This is very useful because it opens the door to enable so-called reactive programming via use of the every keyword. What every does is trigger a block of code for execution upon a value being set on a collection of watched refs. And here we have an example of refs being used as channels. C is equal to A plus B. Whenever ref A or B is updated, C will also be updated. And you see here we have a second every block, which simply triggers and outputs the latest value of C. These are very simple examples, but you could imagine this approach being applied to, say, a self-driving car, or if you worked in finance and had a derivative trading system, you could model the inputs to your calculation as refs and have the output automatically calculated upon a change in those input refs occurring. We can see here that this approach allows us to create individual ad hoc units of concurrent execution. We can also create a reactive graph, and we can create microservices which operate concurrently in order to maximize the throughput of the available CPU cores which we have access to. And as with many aspects of Concurrency code, a compact version of the syntax is provided. We can do reactive programming in just one line of code. This model of concurrent computation is, I believe, easier to comprehend than the standard thread and lock based model of computation, and it opens the door to things like distributed computing, which is effectively an extension to this core mechanic. Now for GPU computing. So to bring everyone up to speed with GPUs, the promise, the dream, the hype, the reality is that with GPUs for many parallelizable algorithms, up to 100 times speed up in performance can be achieved. The promise, the dream, the hype, the reality is that with GPUs for many parallelizable algorithms, up to a 100 times speed up in performance can be obtained versus the same algorithm implemented on a CPU. But this comes with two costs. One is having to code in the likes of C and C++, and two is learning a slightly esoteric program model in order to support the hardware. Concurrency helps a lot with this via its first-class citizen support for GPU computing, as we shall see. Here is a very standard operation upon a pair of vectors, where we are taking every value in A, raising it by a power of 2, adding it to the corresponding value of B, and also adding a constant. And this is the equivalent expressed as a GPU kernel, which can then be run natively on the GPU. Notice how the two are structurally identical. There are only minor augmentations required to the standard function definition in order to achieve this. Getting data onto and off the GPU is a slightly more involved process, but luckily, Concurrency provides a convenient API for doing this, which fits in nicely with the support for isolates and refs exposed elsewhere in the language. Notice here how the write operations return refs. Because the write operation itself is performed in an asynchronous manner, and actually all computation on the GPU can be performed in such an asynchronous manner, and it is the encouraged paradigm to adopt in order to keep the GPU as busy as possible. We are able to copy data to and from the GPU at the same time as computation is taking place. Notice how the GPU kernel we expressed previously has no return type. This is because GPU kernels return function references which can then be passed to devices for execution, like here. Now, given this execution is contingent upon data having been written to these two buffers, we pass the two resultant refs from those write operations to this execution such that it can wait for those write operations to have completed. And finally, we read out the results of execution from the return buffer. Notice here that we choose to use a blocking operation. Thereafter, we can carry on with the execution of the rest of the program as normal. and it is likely that the rest of that program is written in an object-oriented manner, for which Concurrency offers a tremendous amount of support. Here is a standard Java class. Quite straightforward, a bunch of fields, some constructors, some getters and setters, and a mutating operation. Relatively verbose, most people would think. And this is the same in Concurrency. Much less code, much easier to understand, I think. We can, of course, create instances of this class as follows. Notice how the new keyword is optional. We can call methods upon an instance object like this. Concurrency will also automatically map to getters and setters where the assign operator is used. Here, we are using the copy operator, which makes a deep copy of an instance object. For all classes, an equals method will automatically be generated. This defaults to implementing equality by value as opposed to equality by references found in other languages such as Java. Notice here also that the equals operator does what we think it really ought to do and implicitly invokes that equals method. If you want equality by reference, such as in languages like Java, you can prefix the ampersand character to it like this. In the same vein as the equals method, Concurrency also implements a hashcode operator by value. In this way, the following invariant holds. Just like Kotlin, Concurrency is a null safe language. Null safety is built into the type system of the language itself. This greatly helps us to reduce instances of null pointer exceptions occurring at runtime. As such, attempting to assign the value null to a non-nullable type, such as here, will result in a compile time error, not a runtime error, which allows us to write safer, better programs. If one wishes to assign null, one must explicitly declare the type as being nullable, such as here. Attempting to invoke a method or access a field on a nullable type will also raise a compile time error, but sometimes it is quite useful to be able to use null, particularly when using libraries written in other JVM languages. And to this end, Concurrency provides a number of useful operators for achieving this, starting with safe calls. This will invoke the method on the right-hand side or return null if the object being called on the left-hand side is null. Next, we have the Elvis operator, which behaves in a very similar manner. If the left-hand side object is null, we will return the item on the right-hand side. And finally, for those who like to live a little bit dangerously, the no null assertion will throw a null pointer exception if the left-hand side is null. Concurrency also has sophisticated logic to detect cases where nullable type variables cannot logically be null, and in those cases loosens up the requirements. The last topic I wish to cover is as follows. Not every team is made up of just software engineers, and many multi-scheme teams benefit from using domain-specific languages. Concurrency offers first-class citizen support for this. In fact, the following code is perfectly valid Concurrency code. This is achieved via use of a number of interesting features of the language. Here, we're making use of a feature known as expression lists, which essentially allow the dots and parentheses to be omitted from normal state. Here, we're making use of a feature known as expression lists, which essentially allow the dots and parentheses to be omitted from normal expressions. Here, we're taking a function invocation, for example. DSLs are also enabled via use of extension functions. Here, we are defining an extension function on the primitive type integer. And DSLs are also enabled via leverage of Concurrency's support for operator overloading. Here, we have a class definition with the plus and in-place plus operators overloaded. Notice here that we're also using the @ operator in order to create a deep copy of our object created in the previous line. This is another cool feature of Concurrency. Together, these features enable support for domain-specific languages. The final feature I wish to touch upon in this talk is Concurrency's support for what we call language extensions. These essentially allow other programming languages to be embedded within Concurrency code. So, for example, here we have a Lisp-like language. We also have some Fortran, and we have a little bit of APL, which clearly allows us to select 6 unique random numbers from 1 to 40. The language extension functionality permits deep integration between idiomatic concurrence code and language extension code. For example, here we see our language extension is able to access the value stored in variables defined in normal concurrence code. Here we see with our factorial example in APL that this language extension is able to define a function which can itself be called by normal concurrence code. This integration extends to the actual core concurrence compiler. Language extensions are able to interact with the compiler in order to perform compile time checking. They can also report back errors to the user via the standard channels expressed in the concurrence compiler. A very robust API is provided for all of this. Now, I'm often asked about the performance of concurrence code, and it has been benchmarked as being on a par with Java, approximately 5% slower than highly optimized Java code, and this originates from the way in which continuations have been implemented in the language from the isolate and ref-based model of concurrent computation. This is a number which I believe we'll be able to bring down in the future as more optimizations are added to the core language. As it stands right now, though, Concurrency is a very much productivity-oriented language, much in the same vein as Python, and it requires essentially less code to do the same or more work than equivalent lower-level languages. Null Safety is also a nice feature which ultimately leads to safer, better code. And the isolate model of computation, I feel, scales much better than the thread-based model and is a little bit easier for developers and non-software engineers to reason about. And by virtue of the fact that Concurrency is implemented and runs on the JVM itself is always improving, and Concurrency is able to access those incremental upgrades effectively for free. The work which has been done in Concurrency so far represents just the beginning of the journey for the language. There are a number of core areas that current work in the language is focused on, such as improving the GPU support. I think that the model of GPU computing exposed at present is very, very useful, but it could be made a lot more useful for novice developers, people who are maybe not so familiar with the concept of GPU computing. And other features that we wish to add to the language are things like better support for higher order functions. And I feel that that would be very beneficial for even more extensive support for DSLs. On the tools frontier, there is work going on at the moment to provide better IDE support. As far as the core compiler is concerned, the focus of effort in the past has been on generating efficient, optimized code, which runs very, very quickly at runtime. The core compiler itself, though, is a little bit slow, but I believe that there are ways in which that speed can be improved by at least 2 orders of magnitude, relatively easier. On the marketing front, in terms of getting the message out about the language, there is a book which is currently being written, which will be released most likely early next year. There is a Wikipedia entry which is currently in draft form. We need more in the way of secondary citations for that to get out a draft. So if anybody wishes to blog about Concurrency or write an article or video, whatever, that would be very, very welcome. And once that's in place, we'll be able to get some sort of TOBE listing, and we would to start tracking Concurrency on an ongoing basis. There are some experimental features which I like to call labs, which are being investigated at the moment, one of which is known as automatic differentiation. Once this is in place, Concurrency will be the second language, in addition to Apple Swift, to implement this clever technique for performing differentiation. And this is very, very useful for both AI, machine learning applications, but also within the world of finance, so derivatives specifically. There's also some effort at the moment to make use of language extensions for implementing quantum computing, or rather quantum simulators. Concurrency is just at the beginning of its life. Up to this point, it has been an initiative which I've had to mostly innovate for on the behalf of users. But my hope is that future growth for Concurrency will come more from external feedback and also from contributions from the open source community. Further information about the language can be found on our website here. You could also download and play around with Concurrency. We have a REPL command line tool, and it's very easy to get up and running. We also are on the SDK Man platform, so again, very easy and straightforward to get set up. It is an open source project. Here is our GitHub link, and we are very, very welcome of external contributions. And that brings us to the end of our talk. I've been Jason, this has been Concurrency, and remember, this is only just the beginning.
Thank you for your talk, Jason.
Thank you.
And everyone who wants to give you a virtual round of applause can do so in the chat. And if you have a question, you can also write it in the chat now. So far, nobody has asked anything. I guess you gave a great introduction to Concurrency that left no questions open. Okay, then thank you everyone for being here, and thanks again to you, Jason.
Thank you.